What if I told you there's a primality test that's 100% accurate and completely useless? Stay tuned to see why. Here's the wild claim. Pick any integer greater than 1 and let's call it p.
Okay, so just some random p on the number line.
Multiply all the numbers from 1 up to p minus 1. That factorial when taken modulo p equals p minus 1, which is like negative 1 modulo p. And here's the punchline. That only happens if p is prime.
So this single congruence is a perfect primality test? That sounds too good.
Exactly. This equivalence is called Wilson's theorem. Now let's explore why that factorial magically turns into negative 1. Here's why it works when p is prime. We look at the non-zero residues modulo p, the numbers from 1 to p minus 1. Picture them arranged in a circle, 1, 2, 3, up to p minus 1 each represented as a little dot.
Like a clock with p minus 1 ticks instead of 12.
Because p is prime, every non-zero number k has a unique multiplicative inverse. This means there's another number that you can multiply by k to get 1 modulo p. Most numbers are not their own inverse. So we can draw arrows pairing k with its unique inverse, and each pair multiplies to 1.
So all those pairs secretly cancel out to create a bunch of ones?
Exactly. The only exceptions are the self-inverse numbers, those that have a square congruent to 1 modulo p. For a prime, that's just 1 and p minus 1. So the whole factorial 1 times 2 up to p minus 1 collapses to 1 times p minus 1, which is negative 1 modulo p. Let's test it on a small prime and a composite. Take p equal to 5, then 4 factorial is 24, which is 1 less than 25, so it's negative 1 modulo 5. Test passed.
Nice. So 5 really does match the Wilson pattern.
Now try p equal to 6, which is composite. 5 factorial is 120, and that's actually a multiple of 6, so it's 0 modulo 6, not negative 1. So the test correctly rejects 6. In fact, it works for every number. The problem is speed.
Right. For a giant p computing, that entire factorial sounds painfully slow.
Exactly. For large numbers, finding whether p is prime is way easier than crunching 1 times 2 all the way up to p minus 1. Wilson's theorem is a perfectly accurate but gloriously impractical test. A beautiful idea with zero real-world use follow for more elegant math like this. On screen, you can see the two example congruences side by side. Prime passes, composite fails. Please like, share, and subscribe.